Nearly 3/4 of the world is covered by ocean, and at the bottom of the ocean there are huge expanses carpeted with fine sediment. But it's not a featureless and lifeless plain. This track was made by an animal. One of the first explorers of the deep sea was William Beebe of the New York Zoological Society. His steel bathysphere had no cameras. He had to relay his observations to the surface by a telephonic link along the main cable. Nowadays it's different. Deep sea exploration can be done using a whole battery of measuring and sampling equipment. And modern submersibles can operate under their own power without the need for long cables back to the mother ship. Often the most critical and hazardous stage in submersible operations is actually getting the vessel into and out of the water. Submersibles are small and there's seldom space on board for more than 3, a pilot and 2 scientists. Some submersibles can reach the seabed at depths of 5 kilometers or more. Even at 250 meters, it's dark enough for lights to be needed, and you can only see a short distance. It wasn't until the 1960s that scientists began to realize that the ocean floors are not an unchanging feature of the planet. They're being continually renewed by seafloor spreading along the global ocean ridge system. The first direct observation of the seabed in a region of active seafloor spreading and ocean crust formation was in the Rift Valley of the Mid-Atlantic Ridge, near the Azores. This was the French-American mid-ocean undersea study, Project Famous.
At the heart of Project Famous was the actual diving program. Here, geologists could, for the first time, go down into the Rift Valley floor and explore the terrain. Now, geologists in the past, working in the ocean, have always been frustrated. They're really field geologists wanting to walk the outcrop, and they have not been able to do this. They've had to work thousands of feet above the seafloor and lower their instruments and remotely sample the seafloor. But in Project Famous, we had a unique opportunity. We could go down and actually look out of the porthole and see the geology firsthand.
Before the diving program could begin, Alvin had to be modified and tested. On each dive, 2 scientists and a pilot go down to the ocean floor inside a pressure sphere only 6 feet in diameter. The original sphere was made of steel and could only be used for depths up to 6,000 feet. For diving in the Famous area, it had to be replaced by a new sphere made of a titanium alloy.
With our pressure tests completed and the submersible now certified for 9,000 feet, we're ready to conduct our first dive. With everyone inside, the hatch is sealed up and the boat's now lowered fully into the water. With the help of line handlers, we drive ourselves out through the arch of Lulu. We're now completely decoupled from Lulu. The only link is an underwater acoustic phone. After a short checkout, we've been given the go-ahead, we flood our tanks, and the dive begins. You've seen the launch, now put yourself inside the sphere. You blow the tanks, the submarine begins to sink at about 100 feet a minute. It slowly becomes dark. By 1,200 feet, it's pitch dark. And you're falling like a rock towards the floor. It takes you now an hour and a half to sink 9,000 feet. As you near the bottom, you're in total darkness and you turn on your lights. But those lights illuminate only a small area around the submersible. You don't have this magnificent view like you have on the edge of the Grand Canyon. And the problem you have is staring out of the portholes, making observations of a very small amount of terrain and trying to relate those observations to a much larger and global picture. It's like looking at the bark on a tree in a forest. It's crucial that you know the setting of that tree and that you know that you're looking at the right tree so that when you make your detailed descriptions, they have meaning.
As we flew 6 to 8 feet above the bottom, the most common rocks we saw from the submersible were lavas. These had the characteristic pillow shape of lavas erupted underwater, having a rough cracked surface. From the shapes of the pillows, we could recognize and record the directions in which the lava had flowed, and this turned out to be important when we later came to interpret our observations. Mount Venus, for example, turned out to be a series of pillow lavas which flowed away from a central point. In places, mainly towards the margins of the Rift Valley, we could see these pillows infilled or even covered by a thin veneer of sediment. The sediment appeared to be composed of wind-blown clay particles, basalt glass from the nearby pillows, and fecal pellets from the sunlit zone above that had slowly accumulated on the ocean floor. We could also examine some of the structural features of the Rift Valley. The west wall, for example, appeared like an undersea cliff, and at its base we could see rock debris. Throughout the floor of the Rift Valley, we saw numerous fissures that ran for long distances parallel to the axis of the ridge, which cut through the volcanic terrain. Alvin was equipped with a sampling arm, which we used frequently to collect rock samples for the detailed analysis back on Lulu and later ashore. Once on board, the samples were always labeled and weighed, and the precise location from which they were collected was noted. With our accurate navigation system, we knew within 10 to 20 meters where the samples had been taken from.
This is one of the pillow lavas that we retrieved from the Inner Rift Valley during Project Famous. It's very typical in that it's a elongate pillow that's formed as the lava flows out onto the seafloor and is rapidly cooled. It's characterized by an outer coating of glass, which cools very quickly and is in essence a supercool liquid. This glass forms an insulated rind, protecting the interior of the pillow from the cold temperatures. So the magma within the pillow itself cools at a much slower temperature, and as you can see has developed this columnar jointing pattern. In the center of the pillow itself, you see a small conduit, which is the avenue or the path by which the lava is being transported from the vent down the slope of the pillow to the digitations of the ends of the flow fronts. Now, this whole process of pillow formation takes place very rapidly. Now, a volcanic eruption in any particular spot may occur something like once every 10,000 years. But when the volcano is actually erupting, the formation of the pillows is taking place very, very rapidly in a matter of a few seconds to a few minutes.
Scientists have filmed the formation of pillow lavas while diving in shallow water off Hawaii. A new pillow starts as a red-hot fracture in the black crust of another pillow. The crust is less than an inch thick. The new pillow grows at about 8 inches per second. It flows about 7 feet down a gentle slope. Then it implodes. In slow motion, you can see the lava cool and turn black as it leaves the fracture. The pillow grows, but the width of the crack stays the same. Most of the time, growing pillows bend downward with gravity and sometimes break off and tumble down the slope.
In setting up Project Famous, the scientists needed to make accurate sonar surveys of the area before sending down the submersible. This is Gloria. The name means Geological Long-Range Inclined Aztec. It uses sound, not light, to make maps of the seabed. Gloria can be towed behind the ship at speeds of 8 knots or more, and it can map a swathe of seabed up to 60 kilometers across in water depths of 5 kilometers. As Gloria is towed along, an acoustic image is built up on each side. One way of displaying the information is to assemble a mosaic of sonograms from the various ship tracks. The images can be enhanced by computer to reveal all sorts of interesting features, like this meandering channel system, 3.5 kilometers down in the Indian Ocean. This volcano is nearly 4.5 kilometers down on the East Pacific Rise. The summit crater is about 2 kilometers across. Here's the junction of 3 spreading ridge axes in the Indian Ocean at a depth of around 2 kilometers. Color processing improves the contrast. The deep central rift valleys show up blue here. North is at the top. More sophisticated image processing reveals the topography in 3 dimensions. Here's the same triple junction of ridge axes in the Indian Ocean. This time, north is to the left. Wonderful though these pictures are, they can't show you what lies beneath the ocean floor. For that, you need to drill. This is the deep-sea drilling ship, Joy-D's Resolution. The technology of deep-sea drilling has improved a lot since it was first developed in the 1960s. Holes can now be drilled in water depths of more than 5 kilometers. Many drill holes have penetrated through the sediments and a kilometer or more into and through the underlying pillar lavas. The scale of the operation is astonishing. The drill string can be more than 50 times the length of the drilling ship. In the deep oceans, you can't just let down your anchor. The ship is kept on station by side thrusters as well as fore and aft propellers. Signals from an acoustic beacon on the seabed near the drill hole are fed into an onboard computer, which controls the automatic station-keeping system. When the ship drifts off station, the computer activates the thrusters in their proper combination to bring the ship back into position. To get a reliable story out of any particular piece of seafloor, the core must be continuous. But for ease of handling, the core is first cut into 1.5 meter segments. Each segment is sliced down the middle. One half is stored for later research. The other half is studied on the spot, and samples are sent to scientists and laboratories all over the world. Both halves are kept wet until the core has been photographed to provide a permanent record. The white patches in these pictures are calcium sulfate. They indicate periods of desert-like conditions in the area that is now the Mediterranean Sea. The ship's laboratories provide facilities at sea which are every bit as good as anything you can find ashore. There's even a scanning electron microscope to look at microfossils. Sensitive instruments measure the inclination of the Earth's magnetic field when the sediments were deposited. The data provide crucial information about how the continents have moved and the ocean basins have evolved. There are other lines of evidence too. Most of the islands dotted about the ocean basins are volcanic in origin. On closer inspection, you can see that some of them are arranged in more or less linear chains. The remarkable feature of these lines of volcanoes is that they get progressively younger in one direction. How can this be explained?
One way of tackling this is to apply what is known as the hotspot theory. And the best example is the Hawaiian chain. The idea is that under Hawaii there is a hotspot coming up from the deep mantle which causes Hawaii to be active at the present time. Hawaii and the Pacific plate has passed over that hotspot, and so therefore the islands going away in this direction northwestwards ought to be older. They are, and indeed when you come up to this corner at Midway, that's 42 million years old. Look at this. Let's take that as being the Pacific plate. And then underneath it, this is the hotspot, or the thermal plume, and move the Pacific plate over that hotspot. As the plate moves, so the volcanoes erupt, and the record of the plate movement is left in the chain of volcanoes. Change the Pacific plate direction, and still you get a line of volcanoes, but with a kink in it. Once again, move the plate, different direction, volcanoes are still erupting as they're passing over that hotspot, till you come to the present time. And that's the plot. And it's not just been drawn at random. It actually follows, quite precisely, the line of the Line Island volcanic chain. So far as the Line Islands are concerned, the present-day end is here. Come back along it, the volcanic chain gets older and older until you get right up at this end at 135 million years ago.
Impressive though it is, the volcanism of oceanic islands gives an incomplete picture of volcanic activity in the oceans. Most of the activity goes on under the sea. What effect does all this heat have on the water? This is a column of hot water emerging from cracks in the ocean floor. You can see small particles being carried up in the rising water. We're 2.5 kilometers down in the Pacific Ocean, inside the Galapagos Rift Valley. And this is the view that greeted the crew of the submersible Alvin on a dive in 1977. Oases of life in the comparative desert of the deep sea. For several years, scientists had reasoned that hydrothermal vents exist at axes of spreading ocean ridges, and here at last was the evidence. The vent here is at 17 degrees Celsius, much warmer than the usual 2 or 3 degrees found at these depths. This crab is one of several animals making up deep-sea ecosystems centered on hydrothermal vents. Much more spectacular hydrothermal plumes are the black smokers. Seawater at 350 degrees Celsius or more mixes with cold seawater and precipitates sulfides, which build up to form a chimney round the vent. The main reason why these vents are life support systems is not because of their heat, but because of the chemicals they release into the deep sea. At these depths, there's no daylight, so there are no plants to provide the base of the food webs. Animals like this 30-centimeter long fish depend ultimately on bacteria that use sulfide in the water to provide their energy source. The bacteria form the diet of animals like clams and snails, and tube worms like these that can be more than a meter long. The hard white outer tubes protect the soft bodies of the worms inside. These vent systems are ephemeral features. At most, they last no more than a few thousand years. We still don't know for certain how the animals can colonize new vents, which can be tens or hundreds of kilometers from extinct ones. Hot springs are found mostly along ridge axes, where new crust is being formed and the rocks are hottest. As the crust spreads away from the ridge, the rocks cool down, and with time, more and more sediments accumulate. The rough volcanic topography gets progressively buried. Much of this sediment comes from the surface waters of the ocean. These surface waters teem with life. Here, the base of the food web is the phytoplankton, microscopic algae, the grass of the oceans, using carbon dioxide in the water and solar energy for photosynthesis. The phytoplankton are grazed by minute animals, the zooplankton. These, in their turn, provide food for animals higher up the food web, like the sea gooseberry, for instance. Fecal pellets and the remains of dead organisms, along with clay particles, sink and accumulate as pelagic sediments on the ocean floor. The organic remains include the skeletons of planktonic organisms. This foraminiferan skeleton is made from calcium carbonate. So is the coccolithophore. The skeletons of radiolaria are formed of silica. When the sediments are recovered in drill cores, the remains of long-dead organisms can be separated and examined. For instance, the skeletons of foraminifera can be used to work out how climates have changed and current systems have developed with time. Evidence from planktonic organisms helped to date the separation of Australia from Antarctica and the beginning of the Antarctic circumpolar current. When you look at core samples from all over the world, you can see that the remains of marine plants and animals are not the only source of sediment in the ocean. Major rivers like the Mississippi deliver vast quantities of sediments to the ocean each year. This satellite picture shows how plumes of sediment-laden water can extend hundreds of kilometers offshore. Most of the sediment is deposited nearby on the continental shelf. And sediment is carried to the deep oceans by currents that you can't see. They are turbidity currents flowing down the continental slope to the ocean basins. In the 1930s, the Dutch geologist Kuenen showed that dense silt and mud-laden water can carry huge quantities of sediment in suspension. The dense water-sediment mixture acts as a separate fluid, traveling hundreds of kilometers over the sea floor on slopes as low as half a degree or less. They carry more sediment to the deep sea floor in a few days than normal pelagic sedimentation can supply in 1 million years. The flows slow down and spread out and deposit successive layers of sediment to blanket vast areas of the abyssal plains. They form the most extensive flat areas on Earth. Large areas of the abyssal plains are featureless, though ripple marks provide evidence for deep ocean currents. It was once thought that the deep oceans were barren of life. But tracks like these show that there are animals down here. Three kilometers deep, a fish carcass has attracted a great variety of animals. Bony fish with sharp teeth tear at the carcass, and primitive, blind, slimy hagfish scavenge the remains. Brittle stars feed on the detritus. The light is artificial, of course, because it's completely dark at these depths. The animals are attracted to the carcass from far and wide by the smell of food, and perhaps also by the frenzied activity of the earlier arrivals. Even though these animals rarely see the light of day, they look reasonably familiar. Submersible crews have filmed much stranger and more wonderful creatures drifting in the currents of the deep ocean. But that's another story.